Hi, I Aziz welcome you to CoedMaster, and in this video I am going to talk about this problem. So let's get started. So the problem is given as you are given two numbers x and y such that x and y both are greater than or equal to 0 and your task is to raise power of x by y. Let's understand this with an example. Let's say x is 2 and y is 5, then 2 to the power 5 is equal to 32. 5 to the power 0 is 1. 3 to the power 5 is 243 and 6 to the power 1 is 6. Clear? Now let's pause this video and think about a solution to solve this problem. So what you have to do? Basically, you have to raise the power of x by y, right? So let's first see the brute force approach to solve this problem. So in this function, we are simply initializing a result to 1 and we are running a loop from 1 to less than or equal to y. And in each iteration we are simply multiplying x to response, and once the loop gets over we simply returning result, right? So let's quickly dry run this code and see how it works. Let's say x is 2 and y is 5, then the initial value of result is 1. Our loop gets started. In first iteration our I is equal to 1 and the value of result is 2. In second iteration we simply multiply 2 with result. It becomes 2 2s are 4. In third iteration, we multiply 2 with 4, it becomes 8. In fourth iteration, we multiply 2 with 8, it becomes 6. In fifth iteration, we multiply 16 with 2 and it becomes 32. When I becomes 6, our condition becomes false and we come out of this loop. So the output of this function is 32. It means 2 to the power 5 is 32. Now let's talk about the time complexity of this function. So in this function, how many times our loop is running? So it's simple. We are running a loop from 1 to less than or equal to y. It means we are running loop y times. So the time complexity of this function comes out to be theta of y. And this is the exact bound because we are exactly running loop from 1 to y. So this solution is not a best solution because the time complexity is linear and it belongs to linear class of order of growth. So here we have room for improvement and we can obviously optimize this code to make it efficient. So let's see how we can make this code more efficient. So here we have some observation to made. So let's say I want to calculate 2 to the power 4. If I have 2 to the power 2, then it is very easy to calculate 2 to the power 4. I just have to multiply 2 to the power 2 into 2 to the power 2. I will get 2 to the power 4. Similarly, if I want to calculate 2 to the power 5 and if I have 2 to the power 2, then I simply have to multiply 2 to the power 2 into 2 to the power 2 into 2. So this way I get 2 to the power 5, right? So let's use this idea and think about a solution to solve this problem. So let's discuss the idea in more detail. So let me tell you a story. So there is one guy, his name is Joy, and this guy is really lazy. He do not want to do work. He always think of doing least amount of work and he is extremely lazy person. So one day this guy got a problem and the problem is he want to calculate 2 to the power 5. As he is a lazy guy, he thought that if I somehow get 2 to the power 2, then it will be very easy for me to calculate 2 to the power 5. I just have to multiply 2 to the power 2 times and simply multiply 2 to it. Then I will get 2 to the power 2. So what he did, he simply divide the problem into 2 and pass smaller problem to his neighbor. So now the problem reduces to 2 to the power 2. Now his neighbor is also a laziest person. So he also thought of doing least amount of work. So what he did? He again divide the problem into 2 and pass on the smaller problem to his neighbor. And his neighbor is also a laziest person. He also want to do least amount of work. So he thought, what if I get 2 to the power 0, then it will be very easy for me to get 2 to the power 1. So he again divide the problem into half and pass on this smaller problem to his neighbor. Now his neighbor is really smart person. He is not a lazy person like all of them. So now this person know that the 2 to the power 2 is equal to 1, because for any number with power 0, the value of number is going to be 1 always. So this person simply returns 2 to the power 0 to this person. Now this person know that 2 to the power 0 is 1. Now this person has to do simple multiplication. What he did? He simply multiply 1 by 2 and return it to previous person. Okay. Now this person know that 2 to the power is 2. So now this person simply multiplied 2 into 2 to get 2 to the power 2 and returns 2 to the power to the first person. And now finally this person got 2 to the power 2. So to calculate 2 to the power 5, he simply does 2 to the power 2 into 2 to the power 2 into 2 and he get his answer. So the approach we have talked about is called divide and conquer approach. And this approach we generally used in recursion. So here we are basically doing recursion only. This person is calling this person is calling this person, and this person is calling this person. And if I say that all persons are same, then it comes out to be recursion only. So let's see what are the two things we care about recursion. The first thing we care about recursion is in every recursive call we want to do least amount of work, right? And in recursion we want to pass minimum input to a function. Why? To stop the recursion. And we generally call this a base condition. So basically we care about only two things. One is the base condition and second is least amount of work we can do. So let's use this approach in our code and write efficient code to solve this problem. So here this is going to be our efficient code to solve this problem. And this is a recursive call. Now the fast exponential function is making a recursive call to itself by dividing y by 2, right? And y equal to 0 is our base condition. So when our recursive function reaches here, we simply return 1. So when the value of y becomes 0, we simply return 1s. So let's quickly dry run this code and see how it works. Let's say we want to calculate 2 to the power 5. So we call this function first time by passing x equal to 2 and y equal to 5. Now this function makes a recursive call to f of 2 and 2. It means 2 to the power 2. Now 2 to the power 2 function makes a recursive call to 2 to the power 1. And 2 to the power 1 function makes a recursive call to function 2 to the power 0. So function 2 to the power 0 is our base condition. And in base condition what we are doing? If the value of y is 0, we simply returns 1. So we simply return 1 to function 2 to the power 1. Now function 2 to the power 1, the power is odd. So what we do when power is odd, we simply multiply it by 2. Or in case of this function, we simply multiply it by x. So 1 into 2 is equal to 2. So this f of 2 to the power 1 returns 2 to its parent. Now its parent is 2 to the power 2. Now here the value of y is 2. It means it is even. So in case of even, we simply multiply the return value with itself. So it becomes 2 into 2, that is 4. And function 2 to the power 2 returns 4 to its parent. Now f 2 to the power 5 gets the 4. Now the value of y is 5. So it means it is odd. So in case of odd, what we do, we simply multiply 4 into 4 and again we multiply x to it. It means 2 to it. So this way we get our final answer. 4 into 4 into 2, it's going to be 32. So this is how this function works. So we are making a recursive call to itself and we are simply checking if y is even, then multiply temp into temp. If y is odd, then multiply temp into x, right? Clear? Now let's talk about the time complexity of this function. So to know the time complexity of this function, as it is a recursive function, so let's first write the recurrence relation of this function. So the recurrence relation of the time taken by this function is written as time taken by this function is equal to time taken by recursive function plus theta 1, right? And the recursive function is simply taking floor of n by 2 value. And Apart from this, we are simply doing some theta work. So that's why the recurrence relation of time taken by this function comes out to be Tn is equal to Tn by 2 plus theta of 1. Now let's use this recurrence relation and try to construct recurrence tree. So our recurrence tree would look like this. At first we are passing n, so we can write n divided by 2 to the power 0, it means n. And in recursive call we are dividing n by 2, so the power of 2 becomes 1. In next recursive call we are again dividing n by 2, so the power of 2 becomes 2 to the power 2. Again in next recursive call we are again dividing n by 2, so the power of 2 becomes 3, and this process continues till we reach n divided by 2 to the power k, and this is our stopping condition, right? Okay, so now if you see how much work we are doing in each level we are doing theta 1 work. This level we are doing theta 1 work, this level also, and all the levels we are doing theta 1 work. So see, this is the last recursive call, and this recursive call is our base condition. So let's say in this recursive call, in this recursive function, we are going till y equal to 0. Let's assume that we are not going till y equal to 0, we are going only till y equal to 1. Then when we reach this condition, our value of y becomes n divided by 2k is equal to 1. So it becomes n is equal to 2 to the power k, and when we take log both the side, we get k equal to log of base 2 of n. So how much work we are doing basically? In each level we are doing theta 1 work, and we have log base 2 of n levels. So it comes out to be log base 2 of n into theta of 1. So the overall time complexity of this function comes out to be theta of log of n, right? Now what about space complexity? Why we are talking about space complexity? Because it is a recursion based solution. So whenever we write recursive based solution, a recursive call needs space in function call stack, right? So how much space we need? So when we reach here at this point, we are having log n recursive calls, right? So obviously if recursive calls are log n, then obviously we need to store log n calls on function call stack. So the space complexity of this function comes out to be theta of log of n, right? So I hope now you have good understanding about how to calculate power of any number and how to use recursion to divide the problem into subproblems and calculate the final result. So this is it for this video. Thanks for watching. See you in the next video.